In this video, our goal is to describe the behavior of the tip-top in terms of dynamical variable. Let's begin. First thing you should notice is that, during inversion, the angular momentum stays almost along the z-axis. In fact, before and after the inversion, the angular momentum pretty much points in the z direction. During the inversion process, center of mass of the top rises. Wait, from where does this system getting potential energy? Well, the rotational kinetic energy decreases during inversion in order to provide potential energy. This implies that the total angular velocity and angular momentum decrease during the inversion process. But reduction in angular momentum requires the action of a torque. If no frictional force are present, the only external force acting on the top are gravitational and normal force. These forces points along the z-axis. So, these forces can't produce torque along the z-axis. Hence, frictional force must be responsible for the change in the z component of angular momentum. Tip-top is modeled as an eccentric sphere. The instantaneous velocity of the point of contact is dominantly due to precession about z-axis. So, contact point of the tip-top slides into the page, generating a frictional force in the outward direction. The torque due to F acting about the z-axis results in a decrease in z component of angular velocity over time. It is subjected to holonomic constraint. Euler angles. These set of angles are used to describe the orientation of a rigid body. Write angular velocity in terms of EI frame for a symmetric top. Theoretical model. Velocity of contact point with respect to center of mass of top. Projection of this velocity on the xy plane. I'm not showing calculation. Velocity of contact point on xy plane from a lab frame. Sliding friction acts to oppose the motion of point of contact and is proportional to normal force. Here's the equation of motion for xy coordinate. Since F is the only external force acting on xy plane. Equation of motion for z coordinate. Euler's rotation equation describes the rotation of a rigid body from EI frame. After plugging in value, it looks like this. Solution to these equations were obtained using computer. Given initial condition, these are the graph of solution for theta, phi dot and psi dot as a function of time. The top displays unstable behavior during the first half second of motion as psi dot decrease in value and phi dot increases. The sharp spike in phi dot and psi dot are physically less dramatic than they appear.